Welcome to True Projects. In this video, we are going to explain about the project title Comparative Analysis of Deep Learning and Statistical Models for Air Pollutants Prediction in Urban Areas. Introduction. Air pollution has become a critical issue worldwide due to its adverse effects on both the environment and human health. It significantly contributes to increased mortality and morbidity rates globally. Pollutants in the air such as particulate matter PM, nitrogen dioxide NO2, sulfur dioxide SO2, ozone O3 and others have detrimental impacts on respiratory health, cardiovascular diseases and overall well-being. The decline in air quality stems from various sources including industrial activities, manufacturing processes, emissions from transportations, vehicles, airplanes, ships, construction activities generating dust and the combustion of fossil fuels like coal. These factors release pollutants and emissions into the atmosphere, significantly contributing to air quality degradation. Modeling air quality accurately is a complex task influenced by multiple factors. The availability and quality of data play a crucial role in creating reliable models. Additionally, the choice of modeling approaches and techniques such as statistical methods or machine learning based approaches impacts the accuracy and reliability of air quality predictions. The project introduces a novel approach to enhance prediction accuracy by leveraging a combination of meteorological parameters such as temperature, humidity, wind speed, and historical air quality data. This approach involves incorporating lagged air quality features, which means using past pollutant concentration values as predictors to forecast future air quality levels. By integrating these factors, the aim is to refine the accuracy of air quality predictions. The project conducts a comparative analysis between deep learning-based models and traditional statistical models for predicting the concentrations of 5 major air pollutants. These models are evaluated based on their ability to forecast pollutant levels accurately. Deep learning models, known for their ability to capture complex patterns in data, are compared with statistical models like regression or time series analysis to determine which approach yields more accurate predictions for air quality. Objective. The primary goal of the project is to conduct a comparative analysis between deep learning-based forecasting models and traditional statistical models. This comparison specifically focuses on their performance in predicting air pollutant levels within urban areas. The aim is to assess which type of model, deep learning or statistical, proves more effective and accurate in forecasting air pollutant concentrations. The project intends to assess the accuracy and efficacy of various deep learning models such as long short-term memory LSTM and gated recurrent unit GRU. These models are known for their capability to handle sequential data efficiently, making them suitable for time series forecasting. The focus is on using these models to predict the levels of 5 distinct air pollutants: NO2, O3, SO2, PM2.5 and PM10. The inclusion of 5 different air pollutants NO2, O3, SO2, PM2.5 and PM10 aims to test the adaptability and performance of the models across a range of pollutant types. Each pollutant has unique characteristics and sources, so evaluating the model's effectiveness in predicting diverse pollutants help understand their versatility and applicability across various environmental conditions. By comparing the performance of deep learning models such as LSTM and GRU with statistical models, the project seeks to identify the approach that provides the most accurate predictions for air pollutant concentrations in urban areas. The overarching objective is to determine which modeling technique, deep learning or traditional statistical methods yield superior results in forecasting air quality, which have significant implications for environmental monitoring and public health initiatives. Software and hardware requirements. Hardware requirements of the project are operating system of Windows, processor of i5 and above, RAM of 8GB and above, ROM of 25GB and above. Software requirements of the project are: application is Anaconda, primary language is Python, front-end framework is Flask, Backend framework is Jupyter Notebook. Database is SQLite 3. Front-end technologies used in the project are HTML, CSS, JavaScript, and Bootstrap 4. Working modules or flow of work. To implement this project, we have designed the following modules. The first module is importing the packages. This step involves importing essential libraries and packages in the programming environment. These packages usually include data manipulation libraries like Pandas, visualization libraries like Matplotlib and Seaborn, and machine learning frameworks like Keras. Importing these packages ensures that necessary functionalities and tools are available for data analysis and model development. Exploring the dataset air quality data. In this phase, the dataset containing air quality data is explored. This step involves understanding the structure of the dataset, examining the variables, columns, checking for missing values, statistical summaries such as mean, median, etc., and gaining insights into the distribution and characteristics of the air quality data. Data processing. Pandas data frame. The air quality data is structured and processed using the Pandas library, which offers versatile data manipulation capabilities. The dataset is likely converted into a Pandas data frame for easy handling and manipulation. Keras data frame. Additionally, there might be a need to convert the Pandas data frame into a format compatible with Keras, a popular deep learning framework. Dropping unwanted column. During data processing, irrelevant or redundant columns or features that do not contribute significantly to the prediction task might be dropped. This step helps streamline the dataset and improve model efficiency. Visualization using Seaborn and Matplotlib. Visualization is a crucial part of exploratory data analysis. Seaborn and Matplotlib are powerful libraries used for data visualization in Python. Visualizations such as histograms, scatter plots, box plots, and heat maps can help in understanding the distribution, relationships, trends, and patterns within the air quality dataset. These visualizations aid in identifying potential correlations between variables and can provide insights for feature selection and model building. Label encoding using label encoder. Categorical variables in the dataset might be encoded into numerical format using techniques like label encoding. The label encoder from sklearn is employed for converting categorical data into a format suitable for machine learning algorithms, particularly when working with deep learning models. Feature selection. Feature selection involves choosing the most relevant and significant features that contribute the most to predicting air quality concentrations. Various techniques such as statistical tests, correlation analysis, or model-based selection are employed to identify and select the most informative features. This step helps in reducing dimensionality, improving model efficiency, and potentially enhancing prediction accuracy. Splitting the data to train and test for deep learning. Data splitting involves dividing the dataset into training and testing sets. The training set is used to train the model, while the testing set evaluates the model performance on unseen data. For deep learning models, this step is crucial to assess how well the model generalizes to new data and to avoid overfitting. Building the model. This stage involves constructing the deep learning model architecture using a framework like Keras or TensorFlow. The architecture includes defining the layers, activation functions, optimizers, loss functions, and other parameters necessary for the model structure. The model design typically considers the nature of the problem and the dataset characteristics. Training the model. Training the model involves feeding the training data into the deep learning model and iteratively adjusting its parameters, weights, and biases to minimize the loss function. The model learns from the data by making predictions, comparing them to the actual values, and updating its parameters through backpropagation. Flask framework with SQLite for sign-up and sign-in. Flask is a web framework used for building web applications in Python. Combined with SQLite, a lightweight database management system, it's utilized for creating user authentication functionalities like sign-up and sign-in. This likely involves creating user accounts, storing user credentials securely, and managing user sessions. User gives input as feature values. User input their feature values, which represent the parameters or factors affecting air pollutant levels. These inputs are collected through a user interface or form on the front end of the application. The given input is pre-processed for prediction. The input provided by the user is pre-processed to ensure compatibility with the trained model. This involves formatting the input data, handling missing values, encoding categorical variables, and scaling numerical features to match the format used during model training. Trained model is used for prediction. The pre-processed user input is fed into the trained deep learning model to make predictions on air pollutant concentrations. The model utilizes the learned patterns from the training phase to forecast the pollutant levels based on the provided user input. Final outcome is displayed through front end. The predicted outcomes or air pollutant concentrations derived from the model are displayed to the user through the application's front end interface. This user-friendly display presents the predicted values or relevant information regarding air quality based on the user's input. Algorithms used in this project, we have utilized the following algorithms. The first one is ARIMA, Autoregressive Integrated Moving Average. ARIMA is a statistical method used for time series forecasting. It combines three components: autoregression, AR, differencing I, and moving average MA to model the relationship between data points. ARIMA models are effective for capturing linear relationships and patterns in time series data and are particularly useful for predicting future values based on past observations. And the next algorithm used in the project is LSTM, long short term memory. LSTM is a type of recurrent neural network RNN architecture designed to handle long-range dependencies and sequential data. Unlike traditional neural networks, LSTM networks contain memory cells that can store information over extended time intervals. This ability makes them suitable for time series forecasting tasks as they capture and learn from temporal patterns, making them especially effective for sequential data prediction. GRU, Gated Recurrent Unit. GRU is another variant of the recurrent neural network RNN architecture, similar to LSTM but with a simplified structure. GRU networks also possesses gating mechanisms that allow them to selectively update and forget information. They are designed to efficiently capture dependencies in sequential data, making them suitable for tasks involving time series prediction, language modeling, and more. As an extension, we applied an ensemble method combining the predictions of multiple individual models to produce a more robust and accurate final prediction. Comparison graph. This is the accuracy comparison graph. On the x-axis, we have the accuracy score, and on the y-axis, we have the algorithm name. Accuracy is a measure of the overall correctness of a classification model. It calculates the ratio of correctly predicted instances, both true positives and true negatives, to the total number of instances. This is the precision comparison graph. On the x-axis, we have the precision score, and on the y-axis, we have the algorithm name. Precision is a metric that assesses the accuracy of positive predictions made by the model. It calculates the ratio of true positives, correctly predicted positive instances, to the total number of positive predictions, true positives plus false positives. This is the recall comparison graph. On the x-axis, we have the recall score, and on the y-axis, we have the algorithm name. Recall, also known as sensitivity or true positive rate, measures the model's ability to correctly identify all relevant instances in the dataset. It calculates the ratio of true positives to the total number of actual positive instances, true positives plus false negatives. This is the FN comparison graph. On the x-axis, we have the FN score, and on the y-axis, we have the algorithm name. F1 score is the harmonic mean of precision and recall. It is a balanced measure that considers both false positives and false negatives. It is calculated as 2 times the product of precision and recall divided by the sum of precision and recall. It provides a single metric that balances precision and recall, making it useful when we want to consider both false positives and false negatives in the evaluation. Execution. To execute this project, first we need to open the code folder which contains the project source code files. This is the code folder. This is the static folder. This folder consists of files related to CSS, JavaScript and Bootstrap. This is the templates folder. This folder contains all the HTML pages used in the project. It typically includes files like index.html, about.html and more, which represent different pages of the website. This is app.py file. This .py file contains the information related to front-end logic. It includes code written in Python that handles server-side operations such as processing user requests, interacting with the database, and generating dynamic content to be rendered in the HTML templates. This is the model file which contains algorithm information which will be loaded into the project code during runtime. This is notebook.ipynb file. This is the Jupyter notebook file which contains a combination of code, graphs and outputs all in one place. It allows users to write and execute code in individual cells, making it a popular choice for data science. This is signup.db file. This file is the database file used to store user information. First, we need to copy the path of the code folder from the address bar of the file explorer. I'm copying the path. Open the Anaconda prompt. Use the cd command followed by a space and paste the copied path and hit enter. This command is used to change the current directory to the code folder's path. Compile the app.py file using the command python space app.py. So here I'm typing python space app.py and hit enter. This command will execute the Python script and perform a runtime check for any syntax errors or logical issues. After running the app.py file, the Flash framework will host the application locally. At the default address, which is the localhost this and port, which is this. Now copy this local link provided by the Flash framework. I'm copying the link and paste this copied link into any web browser. I usually prefer Google Chrome and hit enter. The homepage of the project is displayed in the browser. This is the front end built using Flash framework. If we are a new user, we need to register first. So click on sign up. So here we need to enter all these details to register. But I have already registered, so click on sign in. So here we need to enter the username and the password which we have created and then click on login. We have logged in successfully. So here we need to enter all these parameters to predict the air quality. So I'm entering the parameters. So here I have entered all these parameters. So here the season is spring. Season represents the time of the year, that is spring or summer. And the value of PM 2.5 is 6.55. It is the particulate matter 2.5 micrometers or smaller, indicating fine inhalable particles. PM 2.5 AQI is 27, air quality index specifically for PM 2.5, indicating the level of pollution for these fine particles. NO2 is 0.9. Nitrogen dioxide, a common air pollutant from combustion processes. NO2 AQI is 1. Air quality index for nitrogen dioxide, indicating the pollution level. NH3 is 0.02. Ammonia, air pollutant mainly from agricultural activities. NH3 AQI is 1. Air quality index for ammonia, indicating its pollution level. CO is 0.11. Carbon monoxide, a gas produced by incomplete combustion of carbon-containing fuels. CO AQI is 1, air quality index for carbon monoxide, showing its pollution level. SO2 is 1.31, sulfur dioxide, a gas produced by burning fossil fuels containing sulfur. SO2 AQI is 1, air quality index for sulfur dioxide, indicating its pollution level. O3 is 1.88. Ozone, a gas formed by chemical reactions involving sunlight and pollutants like NOx. O3 AQI is 1, air quality index for ozone, reflecting its pollution level. VOC is 0.05, volatile organic compounds, a group of organic chemicals that can evaporate and contribute to air pollution. VOC AQI is 1, air quality index for volatile organic compounds, representing their pollution level. AQI is 4.714. Overall air quality index, an aggregated measure reflecting the overall pollution level based on various pollutants, providing an indication for air quality's impact on health. These parameters represent different pollutants and indices used to measure and assess air quality in urban areas, providing crucial insights into the types and levels of pollutants present in the environment. After entering all these parameters, click on Predict. So here we can see we got the result, air quality is good. So we will enter another set of parameters and check the air quality. So I am entering another set of parameters now. So here I have entered another set of parameters. So the season here is summer. PM 2.5 is 156025, that is particulate matter 2.5 micrometers or small. PM 2.5 AQI is 206, air quality index specifically for PM 2.5. NO2 is 20.98, which is nitrogen dioxide. NO2 AQI is 13, air quality index for nitrogen dioxide. NH3 ammonia is 22.48. NH3 AQI, air quality for ammonia is 52. CO carbon monoxide is 2.8. CO AQI, air quality index for carbon monoxide is 33. SO2 sulfur dioxide is 42.58. SO2 AQI, air quality for sulfur dioxide is 59. O3 ozone is 20.14. O3 AQI, air quality for ozone is 20.14. VOC is 10.25. Volatile organic compounds, a group of organic chemicals that can evaporate and contribute to air pollution. VOC AQI is 162. Air quality index for volatile organic compounds, representing their pollution level. AQI is 78.57. Overall air quality index. After entering all these parameters, click on Predict. So here we can see we got the result, air quality is satisfactory. Now we will enter another set of parameters and check the air quality. So I'm entering another set of parameters now. So here I have entered another set of parameters. After entering the parameters, click on Predict. So here we can see we got the result, air quality is moderate. In this way, by entering the parameters, we can predict the air quality, whether it is good, satisfactory or moderate. Now click on Sign Out. The conclusion of the project is, accurately predicting air pollutant levels in urban areas holds immense significance due to its direct impact on global health and the environment. Reliable forecasts allow for proactive measures to mitigate health risks associated with poor air quality and address environmental concerns related to pollution-induced damage. The project involved assessing various forecasting approaches, notably leveraging advanced predictive models like LSTM, GIU, among others. These models, which are part of the deep learning domain, were compared against traditional statistical methods. The consistent trend observed was that the advanced models consistently outperformed traditional statistical approaches in predicting air pollutant levels. This superiority in performance suggests that the potential of these advanced models in improving air quality predictions. The project underscored the importance of continual advancements in the methodology of air pollution forecasting. This includes ongoing improvements in feature engineering, selecting the most relevant and informative features from the data, optimizing model parameters to enhance accuracy, and exploring multi-step prediction strategies. These improvements aim to refine the model's making, them more accurate, adaptable to different scenarios, and ultimately enhancing the reliability of air pollution forecasts. Enhancements in predictive models carry substantial potential to address the broader challenges posed by air pollution. By improving the accuracy and reliability of air quality forecasts, these advancements can aid policymakers, environmental agencies, and health organizations in making informed decisions, implementing targeted interventions, and formulating effective strategies to mitigate the adverse impacts of air pollution on a larger scale. This, in turn, could positively influence public health and environmental sustainability efforts.
Thank you for watching video. For more projects, please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.